这是对。这上面这个是做一下，先要按一下，我确定一下所有。对，然后上面这个就是，我现在是那个红外线。
你那个，你那个，这个位置哦，一般来说这个直播它的
没有开直播，要开直播吗？
没有开直播吗？
不是录影就好了。要开直播的话，我
开一下。也就是上课前就把那个
直播都把它开好，
把它开好，然后把它抛在影像上面。
OK。
Okay, this class is for graduate courses for operating systems. If you are not in the right place, okay, try to find your class.
有在用 Google Meet 还是 Google Meet？
就刚刚那个 Google Meet。你刚刚是 Google Meet？
不是，那是那个13，都是13。
哦，都是13。
对。
13也可以做。
没有，应该不行。
对。
对。你要用你的。
我的跟你用企业的。
对，你用学校的那个。
今天先不要。
先不要。
先不要吗？
对啊，
好，那我们下次。
优先度。
好，没问题。fuck。
The class will be in here every Wednesday, 10 to 12. And because we have another, and these two are our TAs, if you have questions, you can send me your name. And after several weeks, we will have more TAs. The objective of this course is trying to give fundamental concept of operating system design. Not for specific architecture, okay, but focus on multiple processing units, a system with multiple processing units. Okay. The request is you're supposed to know something about operating system, okay, or other related knowledge, okay, in undergraduate, okay. The textbook we will cover some material from these 3 books. Okay. The policy for our grading is that we have 3 written exams, okay, 35% each, so total is 105. Okay. And after that, in the 18th week, we will have 1 makeup exam. So if you feel you are not doing well for some exam, then this part you can sign in for this. Okay, and the score of this one will replace the lowest one of previous 3 exams. Okay. And another thing is that you are encouraged to submit proposal for exam questions, okay, before every exam. Okay. So you study the material, you can create your own question proposal. You can send to me. If I find out the question is good, it may be selected in our exam. Okay? So the purpose is that if you're doing some study, then the result we study, you can submit to me. I will understand what you have learned, and some of the questions may selected from your proposal. Okay? The schedule is something like this. The part 1 is the basic principle. Okay. actually is for most of the undergraduate operating system courses they cover this. Okay, so this part is just for overview. So the material is pre-recorded as a video in EJ201. Okay, so you should be able to look at, study. So the first exam will cover this part. Will be in week 4. Okay. Your proposal for this exam is still in 8th of March. Okay. The second part, we're talking about the systems with multi-processing units. And there's 3 kinds of systems in general. Okay. One is multi-processor system. It means a computer system contains multiple processing units. The second one is multi-computer systems. You put several computers together, okay, connected by a spatial interconnection network. And last one is you connect computers by the network, okay, the general network. And also we will cover the message passing or inter-process communication facilities. Okay. And this part we will cover in class by in-class lectures. And the second exam will be in week 11. Okay. And your proposal is due in April 26th. The last part we were talking about distributed file system and synchronizations. Also, it's in-class lectures. And the exam is due in week 16th. Okay. Proposal due in May 31st. The makeup exam is in week 18th. Okay. So that's the schedule or the requirement for this class. Okay. Any questions so far? Okay. So after this class, the subsequent classes we will have an online version. Okay. And we will record all the material, and also after the class we'll put in EJ3 so you can review after the class. Okay.
你要上哪一个？
第一个
马里 processor
对，你有大陆新的吗？
有。今天早上全部都当到进。
Okay, the part 1 you should study by yourself according to recording the video or any material you can find from the internet, because a lot of good tutorial is in the internet talking about this principle of open systems. So, and here we will start our lecture from the multiprocessor systems. Okay. In general, a system with multiple CPUs have these 3 kinds of basic architecture. Okay? The first one is they have a shared common memory, okay, and attached by several processing units. Okay? That's the typical architecture, and sometimes we call this kind of design as a multiprocessor systems. Okay? And the second possible way is instead of shared memory, okay, every CPU has its individual local memory. Okay, so you can treat these 2 modules together as a spatial computing node. Okay. Maybe it's a board, okay, designed as a computer board, multiple content, memory, and CPU. And then you connect them together by a fast interconnection network. And this kind of typical parallel computer usually designed look like this. Okay? And the last one is every node is a computing power and memory. Okay? And it is an individual computer system, but connected by internet or any kind of general purpose network. So this is a more general architecture for multi-computer systems, okay, or multi-processor systems. We will first discuss this multi-CPU with shared memory, this kind of systems. And this kind of CPU has a basic property is that they have a shared memory for all the CPUs. Okay, so usually, and this, of course, this shared memory may be constructed by several computer memory modules. Okay. And two or more CPUs will connect to this same shared memory together. And another basic idea or characteristic is that all CPU has access to every memory locations in this shared memory. So sometimes we call this kind of system multiprocessor. In general, we can classify this multiprocessor system into two different categories. One is uniform memory access. That means the access time from any CPU to any memory location are the same. Okay? The latency between any CPU to any memory location are the same. Okay? There's no difference. Okay? And the other category is that the memory access time or latency may be different. It depends on the physical location of this CPU and the memory locations. So some memory location from some CPU may be close, and so the latency will be shorter than other memory locations. Okay, so if the memory access latency is not uniform, we call it DUMA architecture, right? And this kind of architecture in general is called UMA architecture. Okay, so CPU may have different access time to different memory locations. For UMA type of processors, the simplest way is you organize the system by using a system bus. So it's a bus-based UMA, something like that. This bus plays the role of the network, connect all the processing unit and memory module together. Okay? And because it is a bus, so the latency between any pair processor and memory module will be the same, okay? Because they all go through this bus, and the latency in the bus identical from any two pair. Okay, so to read a memory, CPU put the address into this bus, and then the corresponding memory module will return its content to the bus. Okay. Of course, this bus usually have two types. One is for address, one is for data. Okay. And this kind of architecture, the advantage is simple, because you just need a fast bus and then put everything connected up. A good bus controller should be able to manage this kind of architecture. the disadvantage is that because it is a bar, so in general, you cannot scale well. Okay, so you cannot connect too many CPU or too many memory modules into there, okay, because then this bus become very heavily, the contention will be too high, okay, because everybody will require this bandwidth. Okay. So the performance is limited by this its bandwidth. So to improve the performance, most of this bus-based UMA multiprocessor would have designed some form of cache. Okay, so we can put a cache in each processor unit or processor module. Okay, so instead of you access every word goes through the bus. Okay, some frequently used location of a particular processor would be cached inside its local cache. That is possible to improve the performance. But in general, this cache usually is not by words, but by a block of words. Okay. A typical is 64 bytes, okay, as a cache block. And here, they use this term, cache line, okay, to represent this block. So what? Any bytes inside this block will be accessed by this processor. Then the whole cache line will be cached. Okay. The reason is locality. Okay, because in general, when you access a byte in some place, the next subsequent access will be to its neighbors. So by using this block or cache line, it's possible it can reduce the number of upload instead of get a byte from memory, you get a block from memory to reduce the total bandwidth requirement. Okay. Because in general, to move a block of bytes from memory to the CPU to the cache is faster than move every byte one at a time. Okay. The total time will be reduced. And another one is after you cache the whole block, your subsequent request or access usually is in the same block. So this kind of design can reduce the bus traffic, okay, the requirement for the bus. It's possible we can get some performance gain. Okay. And this cache may be read-only. Okay, so that means it's possible several processors they all cache in the same block, because if this block or this cache line is marked as read-only, that means you cannot update read-only. The purpose of the cache is for read access only. Then it's possible you can share by several processors. They simultaneously access the same block. It's no problem because nobody is updating that. So, but if it's marked as read-write, that means it's you may need to do some update into that cache line or into that block. Okay. Then it cannot be accessed by other processors. So then the access becomes exclusive, okay, instead of shared, like it's read-only. So you need to do some management for this cache line. Depends on the purpose. Okay, if it's read-only, then it's possible this cache line, several processors will have the same cache line. Okay, because they are doing the read, so no problem for that. Okay, but if any processor try to update, then in general, you need to invalidate other cache lines, only leave the updated cache be the sole cache line on some place. That's all. Okay. To make sure this data consistency, because with multiple processors may take the same block. Okay, we need to, and this kind of mechanism or this kind of problem in general called cache coherence problem. Okay. So if a CPU try to write, and in that particular time instance, the cache line is existed in several places. Then we need to embed the other cache line. Okay, the bus handler must inform all the caches. There's a write request. If this cache is clean, that means everybody is doing the read-only access. Then they just drop. Okay, they can just drop the cache because it comes embedded. Someone try to update after this write request, your cache is not ready. But if the cache is dirty, then the cache must, okay, the processor which hold the dirty cache, that means that particular processor has updated. Okay. It means this the current requester, current write requester, okay, try to access, try to do some write to a particular word. The first thing, they will generate this cache write request to all the possible cache lines. If it is good, that means already been modified. Then the holder of that dirty cache, you can have two methodology to solve that. One is they just flush back this cache line back to the main memory. Okay? And then the requester will get the newest update from the main memory. That's one way. The second way is the holder of this dirty cache, instead of send flashback to the memory, they just send its own cache to the requester. Okay? So the requester will hold the most updated version of that cache line. Okay? And the original holder of this 30-bit cache will discard, okay, after it's sent out and its cache becomes embedded. Okay. Then that's another way. So in general, you have these two possible methodology to make sure that in any time instance, only one writable cache is existing. Okay. But it's possible you can, the system will have readable cache, several readable caches simultaneously, but it only have one writable cache. And this kind of rule usually is used to maintain their consistency. So the memory or the will consistent. You will not miss out, because if you have more than one cache, they all have some update, and eventually you don't know how to merge their results together. Okay? So to maintain cache consistency, the algorithm maintain this in general. We call it cache coherence protocol. If you are interested, there's a lot of literature talking about this. To further improve the performance, okay, because in general, this cache are located inside the CPU module. Okay? They use memory inside CPU, so it's more like a register type of memory, okay, instead of random access memory, okay, in the memory module. So usually, those the size of those cache will not. It cannot contain too many bytes inside a cache. Okay. So another improvement is that not only with the cache inside the CPU, but every CPU you also associate a private memory. Say. So the system may have a shared memory, and each module, CPU module, they contain cache inside the CPU module, but in the CPU chipset, they also contain a small memory module in level, private or private memory. Okay. The reason for this is that when the CPU is executing a process, a process usually contains several segments. You have a text segment containing the instruction. Okay? You may have a data segment containing some data variables, and those variables may be classified into two parts. One is the global variables. Okay? Those global variables may be shared by several threads. Okay? So those global variables should be shared because we may have several threads. They all access this global variable. Okay? But some variable may be private to a thread or a process, okay, instead of shared by several cooperating process or cooperating threads. Okay? So for those data, if the CPU module has its own private memory module, then those can be located in here. When the process or thread is executed by this particular CPU, private information about and read-only segments. Text usually is read-only. Okay? So most modern application design will ask the programmer to write code. We call it re-entering code. That means your instruction, your code will not modify your instruction itself. It will only allowed to modify its data part, not the instruction segment. Okay, so most application design will focus on that. Okay, so the text, the instruction segments during the execution of the process in general, okay, is read-only. You only access. You never try to make update during your execution. Okay. So those parts are read-only segments. Okay. Read-only segment you don't need to put in here, okay? Because read-only that means you can duplicate in another process. In those processes, they all share the same instructions. Okay? And if a multi-threaded process and the system has multiple CPU, each CPU can execute a particular thread. Although those threads, they all execute the same instruction. So those instruction segments can be duplicated in private memory of the CPU. Okay. And also, those private to the computer thread can be put in here. Okay. The reason for that is now this access, you don't need to go through the bus to the shared memory. You only get access directly from your private memory module. Okay, of course, because these are not shared, okay, this CPU and will never access the private memory of CPU1. Okay, the shared memory, all shared parts are in here. Okay. So again, so this kind of design is also UMA, although the latency to shared memory and private memory exit time may be different, but in the programmer, from the programmer's point of view, they only see this. Okay, the cache and the private memory are the hardware support by the system. And management by the operating system. Application programmer, they don't worry about that, they don't care about that. Okay? And this assignment usually is done by compiler. Compiler generate object code if the compiler knows, okay, its hardware has this design, has this capability. Then a good compiler can generate the code to take advantage of this cache and private memory. Okay. So program text, local variable, stack, and other read-only segments, they can be kept in private memory. But the shared part, okay, only for those global and writable shared variables, they will be in shared memory. Okay. So most high performance parallel computer, they will have this kind of design, and together with specific design compiler, they can achieve better performance. So to achieve performance, it not only require architectural design, they also require a compiler, a compatible compiler to take advantage of this architecture. Okay. Because of the limitation of bus, okay, we said the bandwidth of bus, even by the base cache and private memory. In general, this bus-based UMA MPs, the size of in general is under 100 nodes. Okay, typically it's 32 or 64. Okay? If we would like to connect more processors, then instead of using bus, we may use other interconnection network. Right? One particular one is crossbar, okay, switch. N by K, and here in general, most of the cases, this N and K, they can be different, but most systems they may be the same. Okay, so you can connect N CPU module to K memory modules, and this crossbar, every cross point is an electronic switch. Okay, have two states, open or closed. Okay. The cross point IJ, if it is closed, that means iCPU is connecting to GS memory module, okay, when the cross point becomes closed. Okay. So by controlling this cross point, you can make this electron switch pretty low over the connector, so you can dynamically change the connection of the architecture. In general, this crossbar controller, they control the cross point in every instruction cycle. Okay? So, based on the instruction cycles, and every operation are synchronized during the instruction cycles. So for each instruction cycle, the set change the connection of these cross points. And then every module will connect to the desired memory module to get access to that particular, to get the instruction. And then load the instruction after that, you execute this instruction in its CPU. And after the instruction finish, we start the next instruction cycle. The cross point may be changed. It depends on the instruction. The next instruction required from all the CPUs, okay? And they will be set this close point configurations. Okay? And this kind of crossbar switch, because it makes all the any CPU is possible to connect to any memory module, okay? As long as the corresponding close point become close, okay? And we say this kind of network is non-broken. The non-broken it's not saying they never have a conflict. It only means that if CPUs they are accessing different memory modules, when CPUs they access, then they will not conflict with each other. So any two CPU, if they are accessing different memory modules, then they will not conflict with each other and make any contention. Okay? That this is the meaning of the non-blocking. Okay? But if two CPUs try to access to the same memory module, of course there is a conflict. Okay? The close point, only one close point will be configured. So a particular CPU will be selected to connect to that particular memory. The other one will floating, will not connect to that one. Okay? So the non-blocking only means that if CPU access different memory module at the same time, then it's possible. Okay? They will not conflict, generate any conflict, okay, or any contention. Okay. But if two CPU try to access to the same memory module simultaneously, then of course one of the CPU needs to wait. Okay. And the close bar, the size of this close bar, because it's two-dimensional array, right? So it grows in this order of n squared. So again, because of course this close bar cannot be grow too big. So in general, if this multiprocessor system connected by close bar, the size will be limited in around 1,000. Okay. Most typical is 2 to the power 10. Okay. And here is an example of 8 by 8 close bar. Okay. So if you have a CPU module and a memory module, then they will be connected by. And each close point is a switch. Open means there's no connection. Okay. Closed means this one is connected. Then if this one is closed, means CPU 101 now connect to memory module 101. So the access will go through. So if as long as this CPU they are accessing different memory modules, then everybody can get access simultaneously. Okay, depends on how this works. Okay? If for an n by n switch, it means n CPU can simultaneously access n memory module if they all require different memory module. Okay, so this n instruction can go through simultaneously by n different CPUs. Because the limitation of this two-dimensional array, okay, it's a two-dimensional array design. Okay, so in general, it cannot grow too much. Okay. Another type of connection for this multiprocessor system, instead of using the crossbar, we can use a multi-stage switch. Okay. Instead of using the big n by n crossbar, okay, we can generate or construct this multi-stage switch by 2 by 2 switches, another 2 by 2 switch together. Then you can construct a multi-stage network to connect memory module and CPUs. Okay. And this 2 by 2 closed bar, usually you have 2 input with 2 output. Okay. And this switch can simultaneously connect. For example, you can make a input, the upper input go to the upper output, and in the meantime, and B go to Y, okay, or A go to Y and B go to X. Okay. You have these two different states. Okay. And this decision to route the message, for example, when the input from A comes in and which output this message goes through, usually depends on a message header. Okay. Okay. A message header usually has this 4 tuples, 4 fields. The first one is the memory module numbers, okay, the destination memory module, okay, and then the offset inside that memory modules. Okay. The 0 part is the operation, okay, connect to that memory module to this particular location. What kind of operation we try to make is read or write, and then the last one is an option. If it is a write operation, then this data value should be in the okay. So this is a messaging, okay. Then, and it depends on this module number. This close bar usually decide the message input will go to which output line. Okay. Let's see how they work. Okay. One particular organization or construct of this multi-stage network is Omega network. It can be connected by using log-n stages. So you have log-n stages, and each stage require n/2 of 2x2 switches. So total, we instead of using the n² cross point, like for cross bar switch, okay, you use this n/2 times log-n 2x2 switches. Okay. Here we have an n² cross point. So each cross point is a cross bar switch, right? And here we instead of using this cross bar switch, we use a 2x2 cross bar as the built-in point. Then we only need n/log2, n/log2, okay, n times log n/2. This number is less than this one, okay. When n becomes bigger, okay, the number of this will be dramatically less than this n². So it's become possible to build a bigger multiprocessor system by using this multi-stage network. And Omega network, sometimes we call it perfect shuffle. Okay, let's see what is the Omega network. Okay. That means the connector of this, because for an A Omega, that means every stage we have a 4 2x2 switch, and the connection is a shuffle, a perfect shuffle. Every stage is a perfect shuffle connection. Okay. You shuffle this, you take this 4 and this 4, shuffle them together. Okay. So the first one go to this one, and then this one, the bottom up half. The first one will go to the this one. It's like a shuffle, right? You shuffle a deck of cards, okay? And same as all the stage. Only the last stage is a direct connection. Okay? And to make connection between any CPU module to memory module, for example, here, if we try to the CPU 001, try to request the memory of this 001, then they will go through these 3 stages. Okay. The first one is the first connection is 1B, okay, and 1B will look at the destination. The first bit of the destination is 0. Then, so it will go to the upper half output. Okay. Depends on the location, the destination, okay, and the corresponding bits. 0 that means you go the upper half. 1 means you go the bottom half output. output. Okay, and by using this simple routing strategy. Okay, so and then in the second stage to see, look at the second bit is 0 again. So go to the this one. Okay, in the third stage 3A is 1. So using this as output. So the message from 001, the destination is memory module 001. They will go through these 3 stages and eventually arrive. Okay. If it's in the same time, this CPU try to go to memory 110, okay, 011, and then they will. The first connection is 1D. 1D, the 0, that means it go through this one. Okay. Let me see. Okay. 0, 110. So the first bit is 1. Yeah. So they try to go the ray line. Okay. And then the second stage is 1. So using this one. The last stage is 0. So it's 110. Okay. So for this blue line and gray line, they correspond to 2 different CPU to 2 different memory modules. Okay. There's no contention. Okay. But this multi-stage network, okay, unlike the closed bar, if 2 CPU they try to request different memory module, they will never generate conflict. But here it's possible to generate conflict. Okay. Let's see this example. If CPU 111 try to access 100, this one they are all different, right? The memory module are. However, this one they will there is a contention in stage 1D because both requests they all try to use this lower half outputs simultaneously. So only one will go through it. But in this example, maybe the ray line was selected. So this request will go through. Then so this green request will be blocked here. Although their target are different, right? Their target are different, but they may have a contention in some middle stages or middle close bar switches. Okay. So although this multi-stage interconnection network is possible to reduce the size of this connection network, so it's possible you can build a bigger multiprocessor system with more nodes. But the disadvantage is that it may generate some conflict instead of the advantage of closed bar. If the CPU they try to go to access different memory module, then there's no contention. But here, 2 CPU may access 2 different memory modules, but they still is possible to generate contention. Okay. So we take a short break here.
对啊，录完了以后就摆上去。对。这个。这个。谢谢。
不不对，错了，
对对对，下次。
这里。这里发这里。这样。
小时。
这里。
一个签报，全部都签呢。
有什么关系？他们要来上不来上，不来上。这些只是怕到时候考试的时候，我们再借另外一间教室。
到时候再看。然后这个吗？就今天下午，因为我其实下面想说，说这种区块链真的发蛮少，在前2年发比较少。那因为我就想说这篇是代表我，
对啊。
所以我就先用2年来发表论文。然后下面的话，这3篇就是因为我刚才就想到说真的是版面不大，我就想说，不如就是找几篇可以代表老师有用深入强化学习在那个领域有在应用的地方。第一个就是金融嘛，第二个就是那个影像的品质嘛，第3个就是 healthcare 的部分。对，大概是这样。然后我这边就是这3篇在投啦，但是其他的还要再问吗？
就3个就好了。
就这样这3篇。那我们今天下午就是直接用这3篇就好了，还是有什么？
因为我们这边有回去是。
已经还在 under process， 因为我没有拿到，没有收到老师给的或者是那边的回复啦。我看到就已经在 under decision， 我不觉得会上，但是我觉得对，但是他已经写 under decision。我刚有去看 GNCA 的部分，然后对，因为 GNCA 这边有一个问题，就是可能要麻烦老师去处理一下，因为这边我真的不怎么知道怎么写。他submit article 之后，这边会出现一个好，我重申一下。你要跟老师聊？
没有，老你就上一点。
没有，今天上2条节而已。
不是说也是上的。
没有，都是2条字而已。因为前面已经录的那个就对。
好讲，
就是呢，在这登录之后，这边 submit article 这边会有一个这个东西。
就点击一下。那就没有回去，就随便就把它关掉。
没有，它这里面是要填东西，要不然
没有，它不需要全部填，不，你就把全部填就好了。对，全部填就好了。
全部随便填，然后最后上面就好。
对，这个不用填，就写随便慢慢去 export 就好了。OK， 对，因为它这个它就是收集资料了。你就不理它就好了。
这样就好了。
对。
然后那个第句说还有staffing也有，就是他好像是要改，好像半年要更新一次，或者是1年要更新一次，那老师的研究领域之类的东西，所以可能那边也是我去改，
你就改进。
好，
那很不重要的啊。
OK，那我到时候就这样弄。对。然后 GNCA 这边是长这样，因为我看它是 submission fee process， 它就已经到这边了。对，跟那个 IP 眼镜那边不一样。IP 眼镜的话还是 under review， 所以可能这个应该是没有什么机会。
process， 对，它的 status 你看看，它只有这一种，它有哪几种 status？
没有，它就只有这样子。对。因为像是那个 IP 眼镜那边都是这艾斯维尔的那个，他那边就是还在 under review。对，所以因为我看到他们。就我跟着他的这个进度在看，看到他就是经过 edit 之后就直接到 decision influence 这边，所以我是觉得，到时候再去找下一边。
这样，没有问题。
那我们就是下午就直接用这个。还有一件事情是，我听那个昨天曾锦熙有实验室跟我讲说 ，ORC 那个新的东西。 就是好像是高科大。
对，
那
就说你把那个新生的资料给他啊，他去跟他联络说，看有没有人兴趣参与那个，
直接给他就好。
对，
全部的新生吗？还
对，
是
就是还没有进来的。
哦，是下一届。
对，下一届。
那我现在有收到几个？
我不是说有给你吗？
我现在是4个。
对，就是4个。
有一个是共同指导，他是挂在其他老师底下，还是都是在挂在老师？
你只有收到4个，那你去再去问一下系上，啊，问一下那个硕士班的那个助理，让他去问一下。我记得好像不止4个。
因为我记得就是现在，等一下还有那个就是考试的还没有进，还有一些考试，所以我在想老师是不是有一些在后面？
对，前面真是只有4个，后面有申请，
因为我记得3月1号交到就放，到时候才会
所以现在是4个，现在是4个，那你就把那4个的资料给他们啊，你先通知他们说会有姐姐跟他们联络，就是有一个兴趣的。
OK， 那我到时候再把它。
Okay. Okay. So let's continue. The routing in Omega network is just every stage, every switch will check the corresponding bit of the memory request. Okay? And then you just go to according to this bit value. 0, you go to the upper half output. 1, you go to the top. Okay? That's it. And because it can generate contention even 2 requests are not to the same memory module. Okay? It's still possible to generate a contention. So it is a broken network. Okay? The example is we discussed in the last slide. Okay? And because it is a broken network, it's possible to generate contention, okay, even by 2 different packets. So a mechanism we call interleaved addressing mechanism are usually used to name the memory modules. Okay. For example, if the address is word-oriented, that means each access usually started by 4 bytes. It is a word, for example. So you try to access a memory location. Usually, the memory address will be have the last 2 bits will be 0, 0. Okay. So it cannot distinguish the location. So in this way, we usually use the next 3 lower order bits as the memory. For example, if we have a memory module, use this as the memory module's number instead of the first 3 bits, the most significant 3 bits. We use the least significant 3 bits. Okay. Of course, this significant you discard this 2 lower order bits because if the address is 4 byte as a location, it is aligned to 4 bytes. Okay, then these last 2 bits always 0. Okay. The reason for this is that most access, the subject consecutive word access is very common in instructions. Okay, you go to the memory location A, the next instruction usually refer to the n+1 location. Okay. If this access will make the access instead of always go to the same memory module, your next request will go to the different memory module. So the request will become more randomly or more uniform distributed to all the memory modules. Instead of every process, some process they only focus on some memory modules. Okay? The reason for this is that to generate more uniform memory request patterns. Okay? By using this interleaved addressing, it means that instead of using the first significant bit as the module numbers, use the least significant bits. Okay. Then the overall memory request pattern will become much uniform. The distribution will become much uniform because for a program to run, okay, if this sequential program usually use after access location n, the next location will be n+4. Okay, if you 4 byte is a unit. Okay, and so on. So and they will go to the next the different memory modules. Okay, so the access will looping around in this much uniformly distributed in this A memory modules. Okay, or in memory modules. Okay. And this will more likely to make the memory request pattern become much random or much uniform. So the contention possibility will be reduced. Okay. And this is in practice a very useful mechanism to make the access pattern become uniformly distributed into those memory modules. After we discuss this UMA architecture, okay, then another category is the NUMA multiprocessor. It means different memory module will have different latency to different CPU. Okay. In general, they have this. Of course, there's a single addressing space visible to all CPUs. So every CPU can access every memory location. That's the same, okay? But the memory usually classified into two different types relative to a particular CPU, okay? Some memory for a particular CPU will be called local memory, the other are called remote memories, okay? To access remote memory, usually we use this load and store instruction. Okay? You first load the memory location into a closer position, okay, or into cache, and then you can access. Okay? So to access remote memory, usually is much slower than access its local memory. To access local memory is very easy. You just directly go to the memory location because you don't need to move the memory from remote memory and to your local side. Okay? And for NUMA architecture, you can have these two types. One is no cache NUMA without cache. The second one is cache coherent NUMA. That means you have a cache and also this cache are cache coherent. So you have a mechanism, a coherent protocol to manage those caches. So can guarantee their consistency. Okay. Okay. You can see that there is no cache NUMA usually. The performance is not good enough. So that's only ideally exists. No current implementation using this kind of mechanism because you cannot get the performance were not acceptable. Okay, so most systems they use some kind of cache coherent NUMA. Okay, it's a NUMA architecture. Okay. And for this cache coherent NUMA, the most typical way is use a directory-based architecture. To manage those cache coherence. The idea is to maintain a directory database to be called where each cache line is currently in and what status of those cache lines. Okay? Conceptually, this directory-based cache coherent NUMA would look like this. Okay? You may have, in this particular example, we consider 256 nodes system. Okay, so each CPU has its local memory and local bus, and then they connected it by interconnection network. Can be either bus or cross bar or multi-stage network. Okay, either way is all right. Okay, as long as they can communicate with each other. Okay? And a directory. Okay. And the cache is inside here. Cache is inside this CPU. Okay. So if in a particular CPU, the calling instruction requires to access a memory location, which is in its local memory, then you just go to here directly. Right? Go through this local bus. The latency is very short. Okay. If unfortunately this memory access require a memory, for example, in other CPU's local memory. Okay, this memory, although they are local, but they are all shareable. Okay, every CPU can access the remote memory. Okay, also this memory is attached into different nodes. Okay, because using this interconnection network, they can still be accessible, but with different latency. Okay, the only difference is that. Then they need to first send a request to this memory module, and this memory module will look at its cache directory information, and to decide it, okay, we'll move this content of corresponding cache lines back to here. Then this module, after that, they can access. Okay. So the difference is something like this. Okay. Local, you can just move directly from the local memory to its cache line and then access. For the remote, the request will go through the remote, and the remote side will decide it. Okay. Before you can move this cache line to here, depends on the current situation, status of this cache line. If the cache line is already being cached by other node, then this particular node need to invalidate that particular cache line and then make a copy for this new request. Okay? The directory in this particular setup, okay, may here because we have 256 nodes, that means you require 8 bits as the node number. Okay, so this cache line, the cache directory will have 8 bits for the node number and another bit used as a flag to indicate, okay, this particular cache line is cached to particular node, okay, or is currently no cache at all. Okay, it only exists in its local memory. So every node will maintain a directory associated with its local memory, its cache line, and this directory, this flag bit will indicate its local memory is being cached by other nodes, or is currently and no one has cache on it. Yeah? And the 32, assume we have a 32-bit address. Okay, so the total memory size will be 2 to the power of 32 bytes. Okay, and divided by 2 to the power of 8. So every local memory will have 16 megabytes. Okay, 16 megabytes, and each cache line is 64 bytes. So we will have this block number or cache line number will be 18 bits. Okay, and so on. So the memory address will be divided into 3 figures. The first one is the node number. Okay. Second part is the cache line number. And the last part is the offset inside the cache line. Okay. And this is an example for directly in node 36, for example. Okay. And the reason we make this way is that, okay, later we will use this directory in our examples. Okay. The protocol look like this. Okay, look like this. Consider this 256 node. And each node has one CPU with 16 megabytes. Okay, so use 2 to the power of 24 bytes, and also hold a directory of 2 to the 18 entries. Okay, remember this one. Okay, every node has this 2 to the power of 18 cache lines. Okay, and each cache line we require 9 bits to maintain. Okay, the overhead will be something like this. The total size of this directory will be 9 times 2 to the power 18 divided by, this is in bit, so divided by 2 to the power 27 bits. Okay, so the overhead will be this one. Okay. And the total memory will be this. Here is our example. Okay. Assume CPU 20, okay, issue an instruction which this instruction is in here. The address of this memory reference is this, okay, in hexadecimal. Okay. And this address will be split into 3 parts. The first part is for the node number, that will be 36. Actually, is the hexadecimal 24. Okay, and the second part will be cache line is and the last part is 8, okay, for the offset. So you got this address. Because of this, no number is not 20, right? It's not. It's local. That means you reference a memory location which is not local. So the MMU memory management unit of the nodes 20 will send a request to node 36 to check its cache line 4, the status. After receive this, the MMU of 36, okay, will check its cache line 4, check this entry, okay, and because go to here, 4 is 0, so currently no one cache the particular cache line, okay, for this. It's not cached. So you can just fetch that cache line directly from its local memory and send it back to node 20. Okay. And also, in the meantime, we change the status of entry 4 to be marked as cached by node 20. Right? So after this operation, this one become this flag become 1 and this field become 20. Okay. After CPU access, and then the next reference generated by CPU 20, for example, is again go to the node 36 inside cache line 2. Okay. So the request again sent to the node 36. Because cache line 2 was cached by the node 82, right here. So now the MMU will first invalidate, will send a request to inform node 82, okay, that particular cache, this cache line 2. You need to invalidate. Okay. Now the cache will move to the 20, okay, and update the cache to the 20, and also send to us. They either pass this one to not or invalidate. Depends on how you implement this. Okay. This particular library is used inform the 82, and the 82 just send its current content of this particular cache to 20. Okay. Another possibility is you invalidate, and the node 82 will check the cache line is dirty or clean. If it is dirty, then they will send back this 82 to the node 36 to update the real memory location. Okay? And then 36 nodes will send the cache, the updated cache line to node 20. Okay? Depends on how you implement that. Okay? And this directory-based NUMA approach, okay, in this protocol we discussed here, okay, will only allow every cache line only allowed to be cached in one place at a time. Okay, it's not shareable. There's no read-only cache. Every cache is read-write. Okay. The reason for that is it becomes much simpler to maintain the coherence because you always have only one cache. But the reason to maintain multiple cache or readable cache read-only cache is to improve the performance, right? But by using this way, the performance is not too good. So how about It's not possible we can catch a line in multiple nodes. Okay. We left it as an exercise. Okay. You try to figure out design based on this. You try to modify the algorithm. Okay, you may need to add some resource, okay, to maintain other information. So it's become possible to maintain multiple cache lines. Okay. So this multiple CPU, the multiprocessor system, okay, you can have multiple CPUs. Okay. But however, because the current manufacture technology, we can put more gates into a single chip. So the CPU, the design of CPU, even the most complex CPU, they don't require so much gate counts. Okay, so the best way now is we put more CPU, multiple CPU inside a single chip. Okay, that's become the multiple core CPU chips. Okay, because the gate count dramatically increased. And here is an example of processor chip contain 2 CPU core. Okay, we call it in core 1 and core 2 or core 0, core 1. Okay, and each CPU will have its own cache. Okay. And because this always continue to improve, after L1 cache, you still have another gate count available. So you put another layer of cache here, and this is one possibility. Okay, you have an L1 cache is private to particular core, and then you have a shared L2 layer cache which is shareable. Okay, and or if you would like to design this way, it's also possible. You have non-shared L2 cache. That's also okay. The reason for this, why use 2 layers of cache? Okay, if for example, you just put this one a single one, okay, because the technology used are different. Here, the L1 cache is more like a register. It's like CPU register. Okay, it's sending CPU register. Okay, L2 is more like a RAM. Okay, so the design, the design is different. Okay. In general, is because that's why this you can have a more size, bigger size of this L2. Capacity of L2 will be much higher than this layer. Okay. Of course, their latency will be different. This one has shorter latency because it's very similar to register, and this one is similar to RAM, general memory cell. Okay, so the latency are different. Okay. So either way, they all exist in different kind of designs. Okay. The reason for this one and this one is by doing this one becomes shareable. Okay, so these 2 CPU they can compete for this shared L2 cache. Okay. So the utilization of this L2 cache may be increased. Okay. This one need more. If this one the size of this is available, then this particular core, if it need more space, then it's become possible. Okay. And this kind of multiprocessor, sometimes we call it chip-level multiprocessors. Okay. We use this term to distinguish general multiprocessor systems. Okay. That means the CPU chips has multiple cores. Okay. And although they are very similar to general multiprocessor system, because it is they still have some difference. Okay, this shared L2 cage may affect the performance. If some core may hold a lot of cage to hurt the performance of others. Okay, and another difference to the general multiprocessor is that because they are inside the same chip, so some component which is shared by multiple cores. If those components, for example, the power or whatever, those components, they fail, then the whole chip may be crushed. But general MPs, one CPU crush, fail, the others may not be affected. But for this kind of chip MPs, the chip fail, all cores may all fail. Okay? So the failing model is different. Although conceptually they are similar, but their failing model may be different. Okay? After we discuss this multiprocessor architectures, okay, so you have some feeling about a system with multiple CPUs, okay, how they can organize and what kind of design requirements or issues you need to consider. Okay, now let's look at the operating system, okay, of this kind of computer systems. In general, there's three basic approach or mechanism to design operating system for the multiprocessors. The first one is you treat everyone as individual host. So each CPU has its own operating system. That means the shared memory, because they all run the same OS, but with different private kernel data. Okay? For example, you have 4 CPU, they all share the same instruction code segment, but they have their own private data segment. Okay? That means their data structure inside the OS kernel, they are private. Okay? That means every CPU has its own scheduler, and so schedule related data structures, and memory related data structures, and so on. So a process running in this CPU always running in there is managed or generated by that particular CPU, and so on. Okay. So it looks like you have 4 machines. They have their own operating systems. They manage their own resources, and so on. Okay. Although this memory here we only lay out the memory related to operating system. Okay, of course you have a shared memory, a huge shared memory part that's for the user processes. Okay, so the multiprocessor memory will be split into depends on how many CPUs. Every CPU has its own operating system data. Okay. And they are private to each CPU. That's one way. Okay. The second part is we call it master-slave multiprocessors. So you have a special CPU running operating system. Only all operating functions are running by that particular CPU. The other CPUs they are only running user process. Any system call will handled by the particular CPU, and so this particular CPU we call it master, and the other user CPU they only run execute application or user process. They are called slave. Okay? And the last one is the symmetric multiprocess. Everybody can run operating system function and also the user process, but instead of this separate OS data structure, their data structure are shared. Okay. The most modern operating system, the computer system, if they deal with multiple processors, they use this approach. Okay, so it's much common right now. In this type of design, each CPU has its own OS. Okay, the system call can only be called and handled by the particular CPU. Okay? The process generated there, the CPU, the system call will also handled by that particular CPU also. And every operating system has its own table and own set of process of threads. The processes, they cannot, if they are running in two different CPU, they will not share anything. Okay? So it's possible to become unbalanced because a CPU may be idle in the same time other CPU is heavily loaded. It's possible. Okay? And because the memory pages they also is not shared, the page tables are not shared. Okay, so the CPU may have some pages which is has failed. Well, another CPU they are continuous paging because the current running process require more pages, but it has no physical memory or okay, associated. It cannot allocate more memory to its process. So it's also possible. Okay. So this unbalanced situation would become possible for this kind of design. Okay. And because the last one is much critical, okay, because everyone has its own operating system data structure. So for the I/O buffer, they are separate, but the I/O device are integrated, are shared. So it's become possible. One process cache something and update. The other process also cache the same file, same block, same content because they are running by two different operating systems. They will not talk to each other. So the consistency of this storage of file access become the problem. Okay? So the disk access may trigger this inconsistent. We need to have some disk coherent protocol to make sure this will not happen again for this disk buffer or file access buffer. Okay? So that's the problem for this unbalanced and this inconsistent buffering, especially for I/O. Okay, we still have time. And the second one is master slave MP, right? Okay, so we have a special CPU we call master. It runs operating system functionality, all the operating system kernel thereafter are managed. So you have only one single OS, and the memory only half user level, user process. In the other CPU, they only run user process. Okay. So all the system data and all the system call are handled by this one. Okay. Others, they only handle the user process only. So this design is very simple and the performance is good if the size of the system is not too big. Okay. Because if the size becomes too big, then this one may become bottleneck because all the systems go to there. Okay? There's more CPUs than every process running in different systems. They may all generate system calls. So this one become bottleneck. So that's the only problem. Okay. Advantage is simple. Okay. And there's no unbalance because operating system, there are only one operating system, one ready queue. Okay. So you can move around the process easily. Okay. process finishes current task, will generate the system call. Okay. Time content is expired. The operating system will take over, schedule, take over, will assign another process to use the CPU and so on. Okay. So conceptually, something like this. You have a memory, and everybody can access this one. Device handled by this CPU because device goes through this operating system functionality. Okay. The only disadvantage is this one. If this one crash, then the whole system down. Right? Of course, you can have some backup or failure tolerance mechanism. If this one crash, then because the memory is the same, right? So you can have assign another CPU, slave CPU to become the master, right? But you need to go through some recovery process and so on. And also, this one may become bottleneck. Okay. So it works very fine and very efficient if the number of processors are small. So early age of the multiprocessor system, a lot of design are using this approach, okay, because the size is not too big, okay, work fine. Until when you need more CPUs, then you will find out that this become the problem. Okay? This become the problem. Okay? So the last one, symmetric multiprocessor. Again, we have only one operating system, and all the data structure are shared, and every CPU they are the same. They can run operating system function. They can run OS, run user process. Okay. So system code will handled by the CPU, which make it okay. Your process generate system code will handled by that particular CPU. So because the data structure are shared, so data structure for the operating system, they must associate with that. Whenever you try to access kernel data structure, you always go through this lock mechanism. And to make this performance a little bit better, usually we try to organize this data structure according to their functionality. So you can split these OS functions according to their access data structure. So independent critical regions can be designed. So that means when you using inside this critical region, you only use those particular set of data structures. Okay, so it depends on the functionality and the data structure. They can be accessed simultaneously without interfering with each other. Then they can be organized as independent critical regions. And each independent critical region will associate with a lock. So whenever you try to access that, you need to get lock and so on. Okay. So that's most common design for the modern multiprocessor system. Okay. And they have some difficult for this. You need to take care of this, how to split the functionality for independent critical regions. Okay. So each critical region can be executed by different GPUs and without generating conflict. Okay. And also, we need to avoid the deadlock. Okay. To access that, and in general, because avoid deadlock, you have a lot of ways to avoid deadlock. Inside the kernel, the most common way is you assign a predefined order for accessing those data structures. So whenever you try to access data structure, several operating data structure, you always access them in some predefined order. So you will never generate a lock. Okay. So besides the critical region splitting, you also need to take care of data lock. But because it's kernel, it's inside operating service function, you don't have time to detect data or whatever. So the only way is to avoid data. So the most typical way is by doing this. In a multiprocessor system, okay, because you are continually running multiple processes, every CPU running to the thread or particular process. If those threads then require to access some shared data, you need to have a way to avoid race condition, right? So most common way is by using mutex lock. Unlike single or uniprocessor system, okay, you may use the disable interrupt mechanism to achieve mutual exclusion. Right? But for the multiprocessor system, it cannot disable interrupt for all the processors. If you do that, the whole performance will be bring down to become unacceptable, right? But if you only disable a particular CPU interrupt, then this mutex will not be guaranteed. Okay? So in general, we need hardware mechanism to implement this mutex lock, right? A mutual exclusion lock. The most common way is test and say instruction or compare exchange and atomic add and subtraction instruction. They are all possible, okay, to implement. If the CPU supports any of this, then it's possible you can use that to implement this mutex lock. Most current CPU or modern CPU after I think 2010 or even earlier, they use this, okay, compare and exchange, okay, because theoretically they can prove that this one is much powerful than TSSA. Okay, so most modern CPU they use this approach. They have a hardware instruction is compare and exchange, atomic compare and exchange instruction, and then you can use that one to implement. And here we discuss this TSSA because TSSA is much simple. Okay. In uniprocessor system, test and say, of course, no problem because you only have one CPU attach the system bus. Okay, the test and say require, although they require two operations, it's possible you can guarantee that it becomes atomic. Okay. However, if for test and say in even two CPUs, okay, test and say means you read and then you write, you read the content and then write something to the same location simultaneously. Okay. In reality, physically, it's two operation, two instructions, two memory access. One is read, one is write. Okay. So if you have two CPU and the bus operate this instruction first, this, and then do this, and then do this, and so these two mutex, this test and say, will become not atomic. Okay. To make it atomic, we need to make sure when this access goes through, this first instruction goes through, the bus will not be allowed to execute other CPU's instruction until after this one finished. Then, okay. So typically, this test and say implementation in multiple processor system we require to lock the bus when executing TSL, test and say. Before you execute test and say, you lock the CPU, lock the bus, and then you do this too. And then release the lock. So then can guarantee that TSL become atomic. So for this symmetric multiprocessor or the other kind of multiprocessor in this, for example, for master stacker, there's no problem because only one CPU executes the operating system request as long as this master test and save is implemented inside the OS kernel, then it's not used by application or by user process, then there's no problem for this. Okay, but for SMP design, because the OS function can be executed by different CPUs simultaneously, so you need to have special hardware to lock this system bus during this instruction to prevent memory being accessed by other CPU. And by using this test and set mechanism, it's to implement mutex lock. Usually you require bit weighting, right? Because you need to test. If it is already locked, then you continue test. If you test to find out that the original value is unlocked, then your lock will be written right to the lock, right? And then you get a lock. So it's a bit weighting loop, and this kind of loop usually we call it spin lock. Okay, you looping in the while loop to continue to test the status of a particular location, memory location. And in this SMP system, the lock condition will generate a lot of spin. Okay? If a process hold a particular lock for a long time, the other CPU they require this particular lock. Then those process will waste the other CPU's CPU cycle. Just locking, just continue to loop in there. Okay, so the whole system's performance will be bring down by this particular lock. Okay. And also because this spin lock also need to lock the bus. Okay. Every test and say you need to, before execute, you need to lock the bus. And when you lock the bus and you test and unsuccessfully acquire the lock, but during the bus locking time period, the other process they cannot access the memory, right? So the system bandwidth, the bus bandwidth will be bring down also by this spin lock. So this spin lock will slow down other CPU also, because even those CPU they don't require a lock, they still be affected by some process continue to check the lock. Right? So every time you try to check, you use TSL to check the lock. You need to hold the bus, right? So the others will be affected. So that's the reason we need to consider how to avoid this spin lock, okay? Spinning for this TSL design. To improve performance, intuitively you add a cache, okay? But however, if we add a cache in CPU, it will not affect the performance, will not improve, and sometimes it can even bring down the performance even more. Okay, the reason, okay, we have we're out of time for this class, so we'll discuss in the next week. Okay, see you next week.